Hello everyone. Today we will be talking about optical fiber. Okay. Cue things up here. Bring my pretty face on screen. There we go. So let's just start the show on the road. There will be some videos that I'm going to ask you to watch, and they will be in at the end of this presentation, available for you to download for my class. Okay. Okay. So optical fiber, we have talked about the copper links that are widely used in the industry, but we can't have this type of telecommunications course without going into the optical fiber, which is more and more widely used in the industry today. All right, and this is the future of the telecommunications. All right, so what do we see here? First picture. It's a nice picture of a rainbow. What does that mean? That means that a light passes through particles of water, and what happens to the light? Because the light that we're getting is the light that is provided by the sun. So there are two conditions that have to be present in order for you to see the rainbow effect. It has to be raining, and the sun has to be visible at the same time. Where do you see it? You face the sun and you turn around, and it's going to be behind you. Okay. Now let's just take a little bit of a closer look at what happens here, and this has something to do with the light, because optical fiber has to do with conducting light through the medium, and the medium that we use for that is mostly glass. However, there are some plastic optical fibers present as well on the market. Right now, this is basically how you make a rainbow. Right? What do we see here? We see a white light. What is a white light? White light is a light that contains all the frequencies present. All the frequencies are present. Now, when it comes to sound, we distinguish the frequencies by the tone. So the higher tone would be higher frequency, lower tone would be lower frequency. Now, when it comes to light, we distinguish the frequencies of light, because light is particles. Well, there are frequencies, but they're providing their own particles, photons. All right. Now, when it comes to sound uses a medium already that is there. For example, air. Okay, or sound can travel through water as well. Sound will not travel through a vacuum. It's not able to provide its own particles. Light has its own particles, and they are vibrating with their own frequencies, with the frequencies. So what happens when we enter a light from one medium to another? Let's say this is air, and this is glass right here. Right? When the light enters glass, it's a different medium. It is going to slow down. Right? The light travels fastest through the vacuum, which basically is a vacuum, could be considered as nothingness. Right? So there's nothing to slow it down. The light just has a free will to travel as it pleases, and it travels the fastest. Right? Nothing to obstruct the light particles. Right? Now, as soon as it enters some other medium, some other material, of course, the light is going to get slowed down by the whatever material it is. It's still going to travel. Right? Now, if there's this line right here, right, the border between one medium and the other medium or material, the other material, is called an interface. If the light was traveling perpendicularly to the interface, it would not split into colors, but it would just get slowed down. But when the light enters under an angle, then we're going to split the light into different frequencies. Now, notice one thing about what's happening here. You could see that the red light, which covers the lower frequencies of the light, is affected less. It's not as much deviated as the other frequencies, like for example, as the violet light. The violet light seems to be affected the most. When the light slows down, it is going to change its angle of travel. Same as if you would throw a pebble or a rock onto a water, then as soon as it hits the water, it's going to get slowed down and pulled towards the water. Okay, so keep that idea in the back of your mind for now. Right? So the same thing, the light particles, they hit another medium, which is a glass in this case, and so it's going to slow down and change its angle of travel. Right? So this effect we call a refraction, right? Not a reflection, but refraction, and we'll talk about that in the next couple of slides. Right? So the light refracts as it enters another medium, right? And different frequencies will refract in a different way. Why does that happen? Well, it happens because the red light has lower frequencies, which means it has longer wavelengths. The higher frequencies are going to be having shorter wavelengths because it's a higher frequency, it just vibrates quicker, so the wavelength of the higher frequency is going to be shorter. The wavelength of the lower frequency, which would be the color red, is going to have a longer wavelength. Now, the longer wavelengths do not interact with the small, tiny glass particles as much as the higher frequencies. The higher frequencies are affected more by the particles, which means when they're affected more, they're going to slow down more, and the angle of refraction is going to be greater. Okay, so that's what's happening here. So again, the frequencies would be the lower frequencies would be the red, and if we go lower than red, because this would be just visible colors, right? Visible colors to our human eyes. Right? Excuse me, I just came from outside. If we go, well, let's say the medium here would be the middle of things, would be like a green or yellow light. All right. Now, if we go lower frequencies, we're going to go towards the red region, and then if we lower the frequencies more with longer wavelengths, we are going to enter something that's called infrared light. Infrared is lower than red, and it is not visible by us humans anymore, although the frequencies still exist there, and they're still considered as a light. So we can't describe them by colors anymore, but when it comes to optical fiber technical lingo, we are going to describe them by wavelengths. Right? So when it comes to radio waves, we describe the waves, the frequencies by the different waves, we describe them by the frequencies. Right? When it comes to sound, we talk about frequencies. When it comes to light, it just so happens that, yes, we can talk frequencies if we want to, but it just so happens that we talk about wavelengths, right? It's just that the way it is, right? All right, so when we go to the longer wavelengths, we're going to enter the infrared region, but also we can go the other way. If we go higher with the frequencies or shorter wavelengths, excuse me, wow, we are going to talk about ultraviolet. So infrared here or ultraviolet there. And this is where we stop seeing the light frequencies or wavelengths, on the higher frequencies, on the higher spectrum end of the spectrum, and on the lower end of the spectrum, we also stop seeing there. The infrared frequencies also can manifest themselves as heat. We can sense them as heat. Right? There's not much we can sense when it comes to ultraviolet lights, but still they can affect us. Ultraviolet light can hurt our eyes even if we don't see it. Right? Okay, now the frequencies versus wavelengths. Right? So colors, as we say, the frequencies, and wavelengths, we distinguish light by the colors. And here will be the wavelengths. The violet would be somewhere between 380 and 450 nanometers, right? Milli, micro, nano, pico, you get that one. So nano wavelengths. So nano would be at whatever the number is, times 10 to the negative 9th, right? Milli is times 10 to the negative 3. Micro times 10 to the negative 6, and nano would be times 10 to the negative 9 of a meter. Right? Now we go to the other side of things, which when we talk about frequencies. So this would be somewhere around 668 to 789 terahertz. Right? That's a lot of hertz. Now then we go blue, green, yellow, orange, and red. So as you could see, the wavelengths are getting shorter when we go towards the violet light. So shorter wavelengths, of course, they're going to translate into higher frequencies. And the longer wavelengths here are going to translate into the lower frequencies. Yep. So now we get that out of the way. All right. As far as the spectrum here, where are we when it comes to optical fiber transmission? Right? Here's the spectrum and wave of all frequencies of vibrations. Well, not all, but towards the light here. Okay, so visible light right here is somewhere between violet and red. So that's what we can see with our with our eyes. Okay? Now the light goes down towards the infrared region, and that's the frequencies, that's the wavelengths that are being used in this region. These are the wavelengths and frequencies that are being used for optical fiber transmission, right, for signal transmission. Remember this slide right here, the red light is affected less by the medium that it goes through, in which case is glass. And when you go higher frequencies to ultraviolet or violet, those frequencies are being affected more. So obviously, we're going to choose this infrared region because then that light is not affected as much by the glass that it passes through. Right? So that's why this region, infrared region, was chosen for the optical fiber transmission frequencies. Visible light, so somewhere between 400 and 750 nanometers. Different sources are going to be slightly varying in the data that they're going to give you. Now, fiber optic communications typical wavelengths, all right? So the equipment can operate on 780 nanometers or 850 nanometers, or 1310 nanometers and 1550 nanometers. These are the typical communications wavelengths that are being used to transmit a signal. And the signal, as we know, is already, the signal going through the optical fibers is not the electric signal. It's not the electric pulses or waves or vibrations. It is the light pulses that are being sent through the to the link, right? So remember from previous lessons, if we're using LAN configuration with the electric type of signaling going on there, and we have to convert that to another medium, the signal has to use another medium, which would be the light traveling through the optical link. So somewhere in between there, we're going to have something. Remember, it's called a media converter. Right? A media converter in this case would convert the electric signals into the light signals. Okay. Now, in the next lecture, we're going to look at why we actually choose those frequencies and not the frequencies in between. There's a reason why those frequencies are being chosen for the optical transmission. All right. Now we're going to cover something like refraction, reflection, and then the index of refraction and total internal reflection. So these will be the topics that we want to touch on today. All right. Also, when you download the presentation, there's a video here, and I encourage you to click on that and watch this video. I can only give you so much in that hour that I'm spending with you. Now I'm giving you some suggestions to kind of take it a little bit further. And trust me, this is just a drop in the sea that you're getting as far as the whole big picture, but we're gonna start somewhere. So watch these videos that I'm giving you and more in order to get a full grasp, or as much as possible of a grasp on the topic. Right? Now let's talk about a refraction. Remember, let's say there's a light. Excuse me. The light enters. It hits an interface between the air and the. It hits the interface between the air and a glass. So here's the interface. Now this line here that's perpendicular to the interface, it's called a normal. That's our normal. Right? When we deviate from the normal, if the light travels along the normal, it is just going to keep going straight. It's not going to change the angle. It's just going to slow down. Now, when we change the angle, when we deviate from that normal, let's say, for example, 60 degrees in this case, the light is going to hit the interface, and it's not going to travel in the along the line. When it slows down, it is going to deviate from that angle. So we say that the light is going to refract. Okay, refraction. If it would not refract, there are two other possible ways. It could, if the angle is different, it could reflect, bounce off. Or it could travel along the interface. There's something that's called a critical angle. So at some point, the angle is going to be the angle of reflection. And at some point, the angle is going to be angle of refraction. And at some point between those two, between the reflection and refraction, is going to be critical angle when the light is going to travel along the interface. Different materials, different combinations of materials would have different angles that would apply in order to accomplish reflection, refraction, or just traveling along the interface. Right? So that's refraction. All right, over here, see that? Over here, we have another scenario here that the light is being transmitted from this side right now, right? So this is, let's say this is aqueous medium, fancy word, water, watery type of a liquid, right? And over here is air. Now, when you have a angle that is high enough, the light is going to refract from the interface and is going to stay within the water. Now, when you raise the angle, because there's a critical angle, when you get the angle higher, the interface is not going to have enough, I don't want to use the word power, I don't want to use the word energy, it's not going to have enough oomph, all right, to hold the light within itself, and it's going, the light is going to puncture through and it's going to refract. So it depends on the angle. Okay, so when let's say we have a critical angle right here, and the critical angle is when the light is going to travel along the interface. If the angle is greater than the critical angle, this angle right here, the light is going to stay refracted. If the angle is smaller, just like that here, if the angle is smaller than the critical angle, then the light is going to have enough energy to puncture through the interface and refract. There's some letters that say N, that's the index of refraction. We'll talk about that in the next couple of slides. All right. Here is the idea of index of refraction. Different mediums are going to have different angles of refraction. All right. Let's say the light in the, I keep losing my mouse here. It just keeps disappearing on me. Come on, here it is. No, I don't see it. All right. My computer is becoming a little bit stubborn here. It doesn't like, for some reason, it doesn't like the white pages. Let's see if it's going to be easier on if I use the PDF version of this here. Yeah, it doesn't like this slide, right? So what I'm going to do is I'm just going to switch to the to the board here, and let's see if we can do it this way here. All right, and then we're going to continue with the other slides. All right. So let's say we're going to go index of refraction. Right. Here is the here's the formula. N equals C over V. Right. So here's the formula. Let's lower the light a little bit so you don't get as much as my head here. Okay. Now C, where C here is the speed of light in the vacuum. All right, that's the speed of light of vacuum, in the vacuum, and C equals 3 times 10 to the 8 meters per second. So that's quite fast. This is the highest speed that anything can travel, speed of light. Okay. What is the 3 times 10 to the 8? Well, that is like 3 0 0 0 0 0 1 2 3 0 1 2 3 4 5 6 7 8 There you go, meters per second. Right, so that's as fast as the light travels through the vacuum, where there's nothing to slow it down. Right? Now notice that anything you can have the speed of any medium that we're going to travel through this with the light, right, is never going to reach the speed of light in a vacuum unless it is a vacuum. Because anything else than a vacuum, because vacuum is nothingness, anything else in vacuum, we would just deal with somethingness, all right? It will be something. So as long as it's something, then it has particles and it's going to interact with the light and it's going to slow it down. So that V is always going to be slower. So the index of refraction, the highest ever that can be, would be 1, which would be equal to the speed of light. That V is the speed of light through material, whatever that is. Quite often we're going to make it glass, because we're dealing with glass here, right? So, so if you notice, the higher the speed, the more you the more you slow it down, the higher the index of refraction is going to be. So if you have a high index of refraction, the light is going to travel slower through the light. The lower index of refraction, then the light is going to travel faster through whatever the medium is. Okay. Let's see if we can yeah. So this is the next slide that you can see. If V, which will be that, increases, right, speed, then the index of refraction is going to decrease. Right? At the same time, if it decreases, then the index of refraction is going to increase. So higher, so here it would be the, yeah. So if there's a higher index of refraction, the speed of light, the speed is going to go down. So higher index of refractions, higher index of refraction slows down the light more. Okay. Can we see this now? Yeah, okay, I suppose we can. All right. All right, so now we can see the indexes of refraction for different materials. So the index of refraction of vacuum, obviously, is going to equal 1 because of the formula. It will be just a number divided by itself, which is 1. All right. Now, then you see anything else than a vacuum is going to slow down the light. And the index of refraction, the more it slows down, it is going to have a higher index of refraction. All right. And we're talking about the glass right here. Can we see that? Glass. It has about 1.5 of an index of refraction. And I'm getting some distractions here because my laptop is freezing. So I'm going to keep, oh yeah, okay. I can do it like this. Right. Now we have total internal reflection. What do we see here? Let's see if I can do the annotations here. Annotations. Right. Can't even do that, or can I? No, I can't. So you won't be able to see me pointing and you won't be able to see my face. But it's okay. We can continue with the lesson here. Well, you can see where there's a source. The source shines the light inside something that's called a fiber optic link or optical fiber. Now the circle to the right that you see here, the circle to the right that you see, it's basically if you turn that 90 degrees. So if you're looking straight into the optical fiber. The thing that's in the middle, it's called a core. That's where all the light travels through. And the thing that surrounds the core is called cladding. Cladding is basically surrounding, embedding, hugging, something like that, right? So cladding. Now, the core, when the light travels through the core will have a higher index of refraction. The cladding is going to have slightly tiny bit lower index of refraction. 1% is enough. Okay? So there's that sometimes there's the temptation to think that in the core the light travels faster than it would in the cladding. No, actually the core slows it down a little tiny bit. Right? Just to kind of, if you can imagine the cladding that surrounds the core, imagine that it's like a slippery surface towards the light. So the light is just going to bounce off that. If you have enough, if the angle is right, or not the right angle, I don't want to use the right angle. If the angle is proper, which means there's not too much of an angle of an entry into the core, then we are going to have reflection happening. We want to keep that within the core. The light has to be kept within the core. And because of the different indexes of refraction of the core and the cladding, the core has a higher index of refraction, which means the light is going to travel slower than it would normally if you injected that into the cladding. But we don't want to inject it into the cladding. We're injecting it into the core. So because of the differences of the index of refraction, we are creating something like a miniature mirror corridor made out of a mirror inside the optical fiber. If you were able to shrink yourself to the point that you would be able to walk in, which would be, you would have to shrink yourself a lot because the optical fiber is basically thinner than the human hair. And if you were able to walk into that, you would just walk into a corridor that is basically like a mirror walls, right? So that's how the light is being kept, right? So what we have here is that the core has a higher index or refracting index or index of refraction. Then it slows down the light more than the cladding would. Cladding has a lower refractive index or index of refraction, slows down the light not as much as the core would. Okay? Now let's see if I can change the slide and move to another one. How it works. As soon as it doesn't like the video switcher here that I have, it doesn't seem to like the white backgrounds, okay, for some reason. All right, so what do we have here? The transmission is possible if we are able to keep all the light inside the core. So there's a terminology that exists, and it basically says total internal reflection. We want to accomplish that. We don't want the light to escape. We don't want the light to refract. We want all the light that we're going to inject into the core, we want that to be reflected within the core. So excuse me, the transmission that takes place inside the optical fiber is possible if we can accomplish a total internal reflection. Right? We want that light to stay in. And the only way we can make that light stay in the core is that if it does not refract, it doesn't pass the interface into the cladding. We want to keep it in. So we want all the light to be reflected. So the transmission in optical fiber is possible due to something that's called a total internal reflection. Now, we see two optical fibers. The one on the top, it shows single mode fiber. And the one on the bottom, it shows a multi-mode fiber. You could see that the cladding, which is in the blue, that surrounds the core, it doesn't change in size. It's 125 micrometers or 125 microns. The core in the multi-mode is much larger in diameter, around 50 microns. And the core that is in the single mode fiber is much smaller, around 9 microns. It can go as low as 5 microns. Okay? So when we are looking at the single mode, the light, theoretically, that's the idea, that the light travels in a straight line. So that line is called the mode. It's the angle that the light travels through. Right? Now, in reality, it kind of like glides around. So there's a little bit of a kind of a subtle wave happening there. But for the most part, it's considered that the light travels in a straight line. Now, when we are injecting the light into something that's called a multi-mode, the core is much larger in diameter, and the light is injected under different angles. Basically, it's like having a larger light bulb as opposed to a very precise laser beam. Okay, so the single mode basically uses laser sources in order to inject the light. The multi-mode would be using something like a, well, still very expensive, but it would be something like an LED. So it's a little bit bulkier, and it shines the light, well, a little bit wider spread. It's less expensive to produce. So when you see the light beams that are entering at a different angle, they're bouncing off at different spots. So obviously over here, if you look at the single mode, the whole signal is much cleaner on the other end because it doesn't bounce. It's not dispersed. So we could transmit much higher frequencies, and those frequencies are still going to be understood on the other side of the fiber link. Now, when you're going to inject the light into the multi-mode, we can't have frequencies that are as high as if you were having it in the single mode, because the light is going to be dispersed. And it's going to be kind of like muddy, a bit of a light, not as sharp. So we can only go with the frequencies only so high before the signal is just not understood on the other side. It's going to be dispersed. The reason why we're using single mode and multi-mode is the multi-mode is still much less expensive to produce. And if we can get away with that, if we don't need longer distance transmissions, because, well, let's say multi-mode can handle the distances of transmission. Some sources are going to tell you up to 2 kilometers. Some sources are going to tell you up to 3 kilometers. It varies depending on the equipment being used and the company that's publishing the information. But most is going to be at 2-3 kilometers. You're quite safe with that. You will never, well, I wouldn't say never, right? But rarely you're going to encounter distances in LAN configuration, because mostly the multi-mode fibers are going to be used in the LAN configuration. Okay. Now the single mode fiber can transmit signals 50 kilometers. Some sources are going to tell you 100 kilometers without the need to be reinforced or re-amplified. Remember the copper, links, Cat5e, Cat6 that we talked about last time. We're only able to travel with the signal up to 300 feet. Okay, so fiber optics, well, 2 kilometers, a little bit longer distance. All right, now let's see. We have another one. Now it seems to work now. Okay, so the sizes of single mode versus multi-mode would be multi-mode, and I just put some of my own marks here. Let me just. In both cases, the cladding, the size of the cladding that's there, it is going to be 125 microns. So if you're looking at it with your bare eye, you won't be able to tell whether you're holding a multi-mode or a single mode fiber unless you go into use a microscope, and you'll be able to look straight into it, which you should never do if you don't know where the other end is. Because if you should never look straight into optical fiber if you don't know where the other end is. If you're holding a small piece of a optical fiber, just 3 feet long, you know where that other end is because you're holding it, right? Then yeah, you can just put that into a microscope and then look at it, and you're going to see whether this is a single mode or a multi-mode. Now the typical diameter of the core for the multi-mode would be 50 microns, and the typical diameter for the single mode would be 9 microns. Now you can also see 62.5 microns for the multi-mode in the older installations. Then that is kind of being abandoned. You can still get that because some of the older installations are still in place. But the thing to go with right now, it's a 50 microns multi-mode cable. Now, typically for the single mode, typically it's about anywhere between 5 and 10 microns. 9 is the usual thing, all right? But then whenever you're going to use that for installations, you should check what the source is requiring, and you should match the source with the link, right? So that's the sizes of the core and the cladding. All right, so here is another look at the multi-mode versus single mode. Now we're going to look at those OMs, the OM, optical multi-mode, optical multi-mode, optical multi-mode, multi-mode, and this one doesn't say here, but it will be OS, optical single mode, right? So you can see the size of the cladding is always 125 microns. The one that the new standards right now for some years, we're going to use 50 microns for the core, or the older ones would still have 62.5. And then the new ones are 50, right? 50 you can pretty much get off the stock, off the shelf when you go to the distributor, and whenever you need the 62.5 because you encountered some older installation, you should match the equipment. Sometimes it takes a week for you to get it, right? So that's the sizes. That's the sizes of that. Now, how the optical fiber is constructed, for the most part, all right. This is a very basic kind of a takedown of that. So in the middle you have the core, and that's where the light travels. Okay. Then it is surrounded by the cladding. Okay. Now, when we're going to strip the optical fiber in class. We're going to do the fusion splicing. We're going to strip it as low as to cladding. 125 microns. We're not going to strip it any further than that, and even then, it's quite thin. 125 microns, so 125 millionths of a meter, right? So then that is going to usually be covered by something that's called a buffer. It's just for everything else that is going to cover that is going to enclad or basically be built around the core is basically on the cladding. It's going to be for protection, depending on what the use of the cable is going to be, where it's going to be installed. Is it going to be in a nice, dry and warm environment and it's multi-mode for the LAN environment inside the building? It's going to be a different materials that are going to surround. Or if you're going to run that cable between the utility poles outside, that has to withhold the elements like winter, summer, hot, cold, and all kinds of physical hazards, then there's going to be different things that are going to be built around that. So for the most part, so here's a core, here's a cladding that surrounds the core, there's a buffer, which would be kind of a cushioning there, and there's a jacket, and then everything else around it. Different types of cables will use different types of protection. Okay. Is that the last slide? No, that's not the last slide yet. All right, features of them, we're going to cover that a little bit more in the next class, a week from now. So the features of, so these will be the features here on the table. There will be multi-mode versus single mode. Okay, so core versus cladding. We just talked about the sizes. Now, wavelengths that are going to be used within the, and we're going to cover that a little bit more detail next time we see each other, which is going to cover the practical applications of the optical fibers. So the wavelengths, which would be the sort of like, you can say, colors of the light, right? Wavelengths, but those are the colors that we can't see anymore, right? Because when the optical transmission happens in the optical fiber, we can see that, remember, because it happens in the infrared region, which is beyond that we can see. But the frequencies or wavelengths, 1850, 1300, and nanometers typically, and there will be sources, will be LED source, very expensive LED, but still LED. All right, now when it comes to the wavelengths used in the single mode, will be 1310, 1550, and that would be the laser source. Now, this is the source, this is the information that I got from this website right here. Now, as when it comes to optical fibers, sometimes you're going to get slightly different results depending on who's publishing them, all right? Typically, these are the wavelengths that are being used. However, we're going to talk about something that's called the full spectrum optical links that are not limited by the wavelengths. And we're going to talk about why we're using those wavelengths, not the ones in between, in the next class. Then it's pretty much all free game on what frequencies somebody wants to use, right? Bandwidth. Remember, bandwidth is the sort of like an analog signal that can be transmitted through and understood on the other side, up to about 4 gigahertz, right, when it comes to multi-mode, and up to about 100,000 gigahertz when it comes to single mode. So there's a big difference, you know. Distance that you can cover, typically under 2 kilometers. Different sources, some sources might publish that 3 kilometers or so. So basically it depends on the equipment that's being used and all kinds of other things. But somebody said on the first, stay on the safe side here, so they put about 2 kilometers. That's pretty much a long distance anyways when it comes to running cable in a building, right? Now the single mode, it says typically over 2 kilometers. Well, some sources will tell you that up to 50 kilometers without needing to re-amplify the signal. Some sources are going to tell you that up to 100 kilometers you can transmit the signal before they need to re-amplify. So the idea is that the single mode fiber is being used for the longer transmissions. Benefits of that. All right, well, it's less immune to the contamination, the multi-mode, because we're not going as microscopic as the single mode. So it's also less expensive to produce the links, and it uses lower cost equipment that is affiliated with that, right? Single mode is much lower loss, high signal quality, and higher bandwidth, which we just talked about. Applications. Most of the time, the multi-mode you're going to use within the data centers, which would be the LAN configuration, 10 gig, 40 gig, and 100 gig data. Remember, see, this is the signal transmission, up to 100 gigabits per second. And the analog signal will be up to 4 gigabits, okay? So there's a difference between the signal transmission and the bandwidth, right? The digital signal transmission on the bandwidth. Ethernet protocols, MADI, digital audio, MADI stands for multi-channel audio digital interface, closed circuit television, security systems, mostly is going to be used in the LAN applications, all right? Now, when it comes to using the single mode, long haul networks between cities, ENG, electronic news gathering, well, okay, Freudian slip, sporting and live events. So, it's long haul outside broadcast, long haul networks, all the internet between all the communication happens between the cities, intercity communications and so on. They would use single mode because they can transmit the signal over longer distance, right? Now, there are some helpful links, and here are some references. I encourage you to take a look at all the helpful links that I'm giving you here, and I'm going to see you a week from now. They're going to cover part 2, the practical applications. Okay, you have 5 minutes to get yourself ready for Mr. Hager's class, and it was a pleasure to see you again, and I will see you next time. Thank you, guys.